Out on the quiet edge of a distant galaxy, a lonely X-ray lantern shines between the stars, HLX-1, a 20,000 solar mass black hole drifting between worlds. Tonight's journey will follow its slow breath of light from the soft web of galaxies around it, down to the invisible horizon, where time itself bends and stretches. If this kind of cosmic sleep story helps you relax, gently tap like subscribe, and let the channel keep you company on future nights among the galaxies. Hyperluminous X-ray source 1, usually called HLX-1, glows in the faint outskirts of the galaxy, ESO 24349, about 290 million light-years away. It matters because this lonely source offers one of the clearest bridges between small stellar black holes and the giant black holes in galactic centers. Over this documentary, the story of HLX-1 will explain how such a mid-sized black hole can form drift off-center and quietly shape its surroundings. For now, it can be pictured as a pale X-ray lantern hanging above a thin edge-on galaxy, surrounded by a huge volume of dark calm. The simple idea is that HLX-1 behaves like a middleweight gravitational engine, powerful yet distant, sitting slightly apart from the usual rivers of stars. An intermediate mass black hole simply means a black hole of middle weight. On one side stand black holes born from single heavy stars carrying only a few or a few dozen solar masses. On the other side sit supermassive giants in galactic cores holding millions or billions of solar masses like vast anchors in space-time. HLX-1 falls between these extremes, showing that nature can build black holes in gentle steps instead of leaping straight from small to enormous. This middle range matters because it links stellar remnants and central giants, helping explain how huge black holes in galaxies might have grown over cosmic time. In the background of this scene, ESO 24349 stretches across space as a slender edge-on streak, its central bulge wrapped in soft, dusty lanes. The disk appears faint and narrow, like a dim river of starlight seen from the side, while the nucleus glows more strongly near the center. High above this plane offset to one side, HLX-1 occupies a position that seems almost accidental, as though it has been gently lifted away. That offset location hints at a long history of slow interaction, where a small companion galaxy brushed past and was peeled apart by gravity. In this picture, HLX-1 is the surviving heart of that smaller system, still surrounded by a compact cluster of stars. This idea matters because it turns one bright point into evidence for quiet mergers, the unhurried process by which larger galaxies absorb their smaller neighbors. On the largest scales, the host galaxy does not float alone but moves inside a loose gathering of other galaxies bound together by shared gravity. Each galaxy follows a slow path through the group like a ship in a wide dark harbour, its course shaped by a deep unseen gravitational basin. In this environment, small galaxies can wander close to larger ones, stretch into long tidal streams, and gradually dissolve into the halos of their bigger companions. HLX-1 fits naturally into this setting because a stripped dwarf galaxy core is easier to imagine where such close passages and slow collisions are expected. The outer halo of ESO 24349 surrounds the visible disk like a very faint cushion, filled with thin gas-old stars and relics of earlier encounters. Within this halo, loops and trails of material act as quiet delivery routes, slowly guiding gas and star clusters toward HLX-1's off-center orbit. This halo context matters because it explains how a black hole can end up perched above the main disk without calling on sudden violent events. Even so, the region around HLX-1 remains extremely sparse, with distances between stars so large that each one resembles a single lamp on a dark plane. Against that almost empty backdrop, the X-ray glow from the black hole stands out strongly in high-energy light, while staying nearly invisible in ordinary starlight. The contrast between darkness and X-ray brightness acts like a natural spotlight guiding modern observatories toward a region that otherwise would seem unremarkable. HLX-1 first drew careful attention through these X-ray eyes, its outbursts appearing as rises in brightness against the steady quiet of the host galaxy. Over many observing seasons, these outbursts have followed a slow rhythm, brightening and fading on timescales of months to roughly a year. That repeating pattern matters because it resembles the behavior of smaller black hole systems in the Milky Way, suggesting shared physics across very different mass scales. This behavior points to a flow of gas spiraling inward toward the black hole, sometimes steady, sometimes enhanced, yet always governed by gravity. In this opening stage of the story, the detailed structure of that flow can remain in soft focus, like machinery seen through slightly frosted glass. What stays clear is the calm message that familiar processes appear to operate in HLX-1 even far from home, and at much higher luminosities, from the surrounding galaxy group down to the halo, and from the halo down to the off-center orbit. Each layer supports the view of HLX-1 as a mid-sized anchor. The path inward through those layers will continue in later sections, but the tone remains slow and even, favoring gentle understanding over urgency. Each step is meant to feel unhurried, so that the large-scale structure and the intimate zone around HLX-1 merge into one continuous steady landscape. For this first section, it is enough to hold a simple picture of a thin edge-on galaxy, crossing the dark, and just above its midline a small persistent point where gravity and light quietly work together around HLX-1. On scales larger than a single galaxy, HLX-1 lives inside a gentle web of shared gravity and drifting matter. This shared environment feeds it slowly over immense stretches of time. Around ESO 24349, other galaxies move through the same region, each one wrapped in its own faint halo of stars and gas. A galaxy cluster is a loose city of galaxies bound together by an extended pool of unseen mass. That pooled gravity matters because it guides long curved paths for galaxies' star streams and thin veils of gas. Over hundreds of millions of years, these orbits bring systems close enough for gentle tugs and slow exchanges of material. In this wider frame, HLX-1 becomes part of a quiet circulation of matter through the group rather than an isolated oddity. The cluster environment fills space with a very thin intracluster medium, a hot rarefied gas between galaxies. This tenuous medium matters because it can strip gas from small galaxies and soften their edges as they move through the cluster. As those smaller systems lose material, streams of gas and scattered stars are left drifting like faint trails of smoke along their orbits. Some of these trails pass through the outskirts of larger galaxies, adding to their halos and feeding slow, long-term changes in their structure. ESO 24349. As one inhabitant of this environment moves through this hot medium and through these trails at a steady, unhurried pace. Its own dark matter halo, a wide, invisible cocoon of mass, extends far beyond the visible disk and bulge. That halo matters because it deepens the local gravitational well, making it easier to capture passing debris gas clouds and even compact star clusters. When a small companion galaxy drifts too close, tidal forces can stretch it into a long tidal stream, a drawn-out ribbon of stars. Over time, much of that companion can dissolve into the halo of the larger system, while its dense core survives and continues to orbit. HLX-1 fits well into this picture, if it is the heavy heart of such a former companion, still circling within the extended halo. In that case, the group environment supplies not only the original dwarf galaxy, but also the gas and stars that now surround the black hole. Even without a complete merger, Slow interactions can thicken or twist these streams, adjusting the pathways that bring fuel into the region of HLX-1. From a distance, the cluster web can be imagined as a dim lattice, where galaxies sit at crossing points of very soft filaments. Along those filaments, gas and dark matter flow inward, though the motion is so slow that it remains invisible on human timescales. This slow inward drift matters because it ensures a long-term supply of material to group members, preventing them from becoming entirely cut off and starved. For HLX-1, such flows offer a background supply from which local structures like its associated star cluster can draw. Within the halo of ESO 24349, small clouds of gas may move on elongated orbits, some reaching far above the galactic plane. When those clouds pass near the compact cluster around HLX-1, a fraction of their gas can be captured and pulled inward. The process is gradual and inefficient, yet it does not need to be fast to matter over millions of years. A thin trickle of captured gas can be enough to maintain an accretion disk punctuated by periods of slightly higher inflow. The observed outbursts of HLX-1 then become one natural expression of this slow supply line rather than a sign of chaos. In this view, nothing about the environment needs to be violent or extreme. Each outburst is like a momentary brightening of a small lamp in a vast dim hall powered by fuel delivered by very patient couriers. The surrounding galaxies continue their paths almost unaffected their own stars, and gas only gently reshaped by the shared gravity of the group. This calm setting matters because it reassures that even the most luminous events seen from HLX-1 are embedded in a broader stable structure. As the story moves inward in later sections, this web stays in the background, holding the host galaxy and its black hole in place. The cluster, the halos, and the drifting stream together build the stage on which the detailed physics of accretion can play out around HLX-1. In that stage, gravity acts less like a sudden pull and more like the soft slope of a huge basin. Orbits become slow-stretched loops that keep stars' gas and compact remnants gently circling rather than crashing together. This pattern matters because it allows HLX-1 and its surroundings to evolve through many small adjustments instead of rare dramatic events. Over time, these small adjustments guide matter from the loose cluster web into the firmer grip of the galaxy, and finally into the halo. The next inward step follows that guidance, moving from the shared cluster gravity to the deeper, quieter pull of the dark matter halo around ESO 243-49. On the scale of a single galaxy, the deep halo around ESO 243-49 quietly sets the rules of motion for everything moving inside it. This idea is simple and gentle. The unseen halo decides how stars, gas clusters, and compact remnants are allowed to drift long before they ever feel the crowded brightness of the inner regions. The halo itself is an extended cloud of dark matter that stretches far beyond the disk and bulge that appear in visible light. It does not shine, yet its steady gravity keeps the galaxy and its companions bound together over billions of years. In this soft framework, HLX-1 and its star cluster travel as one small heavy bead, sliding within a wide invisible bowl. The path of that bead is not random. It is shaped by the overall mass of the halo, by slow tidal tugs from other galaxies in the group, and by the long history of mergers that have fed ESO 243-49. In the outer parts of the halo, orbits are often stretched and elongated like wide ovals drawn in very thin ink around the galaxy. Small galaxies, star clusters, and gas clouds can spend immense periods of time near these outskirts, lingering far above or below the galactic plane before slowly drifting inward again. When a small companion galaxy moves close to ESO 243-49, the difference in gravity between its near and far sides creates a gentle, persistent stretch. Over time, that stretch pulls the companion apart into a tidal stream, a long ribbon of stars and gas drawn out by uneven pull. The ribbon wraps partway around the larger galaxy, its stars continuing on paths that still remember the original orbit. While the loose outer parts of the companion are lost to the halo, the most tightly bound region, its central core, can survive as a compact remnant. HLX-1 fits naturally into this picture as a massive black hole embedded in such a surviving core still attended by a relatively dense star cluster. This setting matters because it offers a calm way to place a 20,000 solar mass black hole far from a galactic center without needing a violent kick or explosive event. Instead of being flung outward, the black hole arrives in the halo through slow orbital evolution and gentle tidal stripping. During this long dance, the dark matter halo acts like a broad, shallow valley in the gravitational landscape. Any object inside this valley must follow paths largely set by the overall mass distribution rather than by local details alone. Gas clouds moving through the halo experience gentle changes in energy as they interact with the thin circumgalactic medium or pass near other clouds and streams. Each close approach or drag effect nudges their orbits very slightly, like a soft touch on a rolling ball. Over tens or hundreds of millions of years, these tiny nudges can add up. A cloud that once orbited at the far edge of the halo can slowly sink inward, its path tightening and its speed adjusting to the deeper gravitational region. Some of this drifting material may eventually pass near the orbit of the star cluster surrounding HLX-1. When that happens, the combined gravity of the black hole and the cluster can capture a small share of the passing gas. In the quiet language of gravity, the halo provides the broad stage while the HLX-1 system behaves like a small basin carved into that stage, ready to receive whatever drifts close enough. Stars in the halo follow similar slow stories. Many travel on wide loops that carry them far above and below the midplane of ISO 24349. Some likely belong to the same original dwarf galaxy that brought HLX-1 inward, still forming a loose ghostly association of related stars. Others come from the main galaxy itself, scattered into the halo by older tidal encounters, or by the gradual heating and thickening of the stellar disk. Together they create a sparse stellar background, in which the HLX-1 cluster stands out as a slightly denser knot of light. That contrast suggests that the system is not just a lonely black hole, but part of a small self-contained structure that still holds its own identity. Indications that the cluster around HLX-1 may be relatively compact and young compared with the oldest halo stars add another quiet hint. Even in the low-density environment of the halo, new stars can form when gas is compressed along tidal streams or wherein falling clouds collide and cool. During the stripping and settling of the original companion gas near the embedded black hole could have been squeezed enough to ignite a fresh generation of stars. In that case, the cluster serves as a living record of the merger, holding both the heavy central black hole and a local group of stars born during or after the encounter. The halo in this view does more than simply hold the galaxy together. It writes slow, sweeping rules that decide where dense cores clusters and black holes like HLX-1 finally come to rest. From those resting places, finer scale processes such as accretion radiation and mild feedback can unfold without disturbing the large-scale calm of the halo itself. The overall picture remains slow, steady, and deeply shaped by gravity. The next step in this journey moves from the diffuse grip of the halo into the more structured outskirts of the visible galaxy, where the edge on disk bulge and dust lanes of ISO 24349 begin to shape the immediate surroundings of HLX-1. The visible parts of ISO 24349 now offer a sharper frame for understanding where HLX-1 actually resides. In simple terms, the galaxy's shape and orientation explain why this black hole seems both connected to the system and strangely detached from it. ESO 24349 presents itself as an edge-on lens of starlight with a bright central bulge and a thin, flattened disk stretching outward on both sides. In this view, the main body of the galaxy resembles a narrow, glowing bar laid across the sky. Most of its stars are compressed into a slender band. HLX-1 does not sit within that band. Instead, it appears displaced above the plane, offset from the visible midline and away from the obvious centre of mass. That offset position matters because it signals that HLX-1 is not part of the usual nuclear cluster or central black hole. It is more likely linked to a captured core moving through the outskirts of the galaxy. It lies far enough to be clearly off nuclear, but close enough that its orbit remains deeply tied to the host. This combination supports the idea that HLX-1 rides along with a compact star cluster, or stripped nucleus, embedded in the outer regions of ESO 24349. The edge-on orientation of the disk plays a quiet role in this picture. Because the galaxy is seen from the side, the disk's thinness becomes obvious. Any object significantly above or below the plane stands out more clearly against the background. HLX-1 perched above that narrow ribbon of stars becomes easier to distinguish in high-energy images, especially where dust absorbs or scatters optical light. Dust lanes, which obscure parts of the bulge and disk, do not blanket every line of sight. Instead, they form patchy curtains that can hide some features while leaving others untouched. HLX-1 likely sits in a region where dust is relatively sparse along the line between the source and the observer. This partial clearing matters because it allows optical and ultraviolet observations to pick up traces of the surrounding star cluster. At the same time, the main signal from the black hole still arrives in X-rays. From this vantage point, the outskirts of ESO 24349 can be imagined as a layered scene. The bright bulge dominates the center, the thin disk extends outward and above that disk, HLX-1, and its companions trace a separate higher path. Stars in the outer regions follow orbits that may tilt relative to the main plane. Some may also warp slightly if they originated in a smaller galaxy brought in at an angle. These tilted paths help explain the projected height of HLX-1 above the disk. A remnant core on an inclined orbit naturally climbs above and below the visible midline as it circles the galaxy. Over many orbits, this motion forms a gentle loop in 3 dimensions. In projection on the sky, it appears only as a modest offset. In the galactic outskirts, stellar density is lower than in the crowded central bulge. The light from the disk still provides a faint background, but individual clusters and compact knots can be picked out more easily. The HLX-1 cluster takes advantage of this lower crowding. It shows itself as a small distinct concentration against a comparatively clean field, at least in the wavelengths where dust has less influence. In that sense, the galaxy's geometry and dust distribution act together like a natural spotlight and filter. They separate HLX-1 from the main body just enough for its character to be studied without ejecting it from the gravitational family of ESO 24349. This balance matters because it lets observers probe an intermediate mass black hole in a setting that is neither fully central nor truly isolated. The outskirts also experience weaker tidal forces from the galaxy's core. Here the gradient in gravity is gentler, so a compact cluster has a better chance of remaining intact as it orbits. That environment is friendly to a surviving dwarf nucleus carrying a heavy central black hole. It can orbit for a long time without being completely shredded, even as stars are slowly stripped or exchanged. Over millions of years, the cluster may lose some members to the main galaxy, while also capturing a few newcomers from the surrounding halo. The result is a mixed stellar population that quietly records the history of its interactions. In this calm setting, HLX-1 appears less like a rogue object and more like a long-term guest in the outskirts of ESO 24349. The luminous central bulge and the thin disk provide a stable background, while the halo connects the galaxy to the larger group environment. HLX-1 and its cluster occupy the space between these elements in a zone where all three influences overlap. The next inward step moves closer to the gas and debris that flow through this region. It examines how the circumgalactic medium and the outer interstellar medium shape the pathways that bring matter into the reach of HLX-1. Around ESO 24349, a broad halo of gas surrounds the galaxy and fills the space between stars and satellite systems. In simple terms, this thin atmosphere acts as a quiet supply line linking the outer group environment to the regions where HLX-1 moves. Astronomers call it the circumgalactic medium, a very diffuse halo of gas bound to a galaxy. It can be pictured as a faint fog that stretches far beyond the bright disk and bulge. Within this fog, the remains of past encounters drift as long curling streams of gas and debris. These streams remember earlier mergers in their twisted shapes, even when their original galaxies are gone. The circumgalactic medium matters because it slowly guides gas toward the host, while still letting it roam at large distances where HLX-1 now travels. Much of this gas stays hot and rarefied, warmed by gravity by motions inside the group, and by ancient episodes of star formation. Scattered through it are patches that cool and condense, forming slightly denser clouds inside the broader haze. These clouds are like small knots in a loose fabric sliding along gravitational paths that loop around ESO 24349. Some knots stretch into long filaments that wrap partway around the galaxy, tracing the slow tracks of earlier encounters. Other knots fragment into smaller clumps that wander for long periods before finally settling into deeper, quieter orbits. As they move, some clouds brush against tidal streams or other clumps, and gentle collisions compress parts of them even further. Compression increases density, helps gas cool, and encourages the growth of narrow filaments and compact knots. Over long timescales, these structures slowly sink deeper into the halo, drifting toward the outskirts of the visible galaxy. In the region where HLX-1 resides, this mixture of hot, warm, and cooler gas creates a layered background. The black hole and its star cluster move through that background along their orbit, passing through patches of different density and temperature. That motion matters because it decides how much fuel is available in the immediate neighborhood of HLX-1 at any given time. When the orbit carries the system through thinner regions, there is very little material to capture. During those passages, accretion remains weak, and the X-ray glow stays modest, like a distant ember rather than a sharp flare. When the path crosses a denser streak of gas, the picture changes in a calm but important way. The combined gravity of the cluster and the black hole tugs on nearby material. It slows some of the gas until it can no longer follow its previous trajectory. A small fraction of the gas becomes bound and begins to spiral inward instead of continuing past. The flow resembles smoke caught in a slow eddy, turning gently back toward the center rather than moving straight on. Even if each encounter captures only a tiny share of the nearby gas, the effect accumulates over many orbits. The circumgalactic medium then acts not only as a background, but as a long-term reservoir that quietly tops up the supply of inflowing matter. HLX-1 does not need a single dramatic event to feed it. It relies instead on repeated, modest interactions with gas that is already present in the space around the galaxy. Different temperature phases of this gas reveal themselves in different kinds of light. Hotter parts glow faintly in soft X-rays, while somewhat cooler regions leave delicate absorption imprints in ultraviolet light when they lie in front of brighter sources. Together, these signals trace out partial maps of the pathways through which matter moves around ESO 24349. Those maps matter because they show that the region of HLX-1 is not empty, even though the visible stars there are sparse. Rather, the system sits inside a slow river of gas that sometimes thickens into clouds and sometimes thins almost to a vacuum. Along this river, the star cluster around HLX-1 acts like a small harbour on a wide, quiet coast. It cannot gather every passing parcel of gas, but it can collect enough to maintain a changing, flickering flow. The long intervals between strong outbursts then fit naturally into this scene. They point toward a fuel supply that is modest, intermittent, and governed by the broad dynamics of circumgalactic gas instead of by sudden explosions. Over millions of years, the same gentle processes redistribute energy and matter throughout the halo. Heat spreads outward from motions and shocks, while cooled clouds sink inward or are reshaped by further encounters. Inside this ongoing circulation, HLX-1 behaves as a compact sink, turning a fraction of the inflowing gas into radiation and perhaps small outflows. The next inward step follows this gas as it leaves the circumgalactic halo and enters the denser interstellar medium in the galaxy's outskirts. The interstellar medium is gas and dust filling space between stars. In that zone, dust stars and magnetic fields begin to guide its journey in more intricate ways. Dust in and around ESO 24349 shapes how its light escapes and how HLX-1 is seen against the galaxy. The simple idea is that dust chooses which wavelengths pass through clearly and which are softened or blocked, so each kind of light gives a slightly different portrait of the same region. In visible light, the galaxy's bulge and disk appear crossed by dark lanes, where dense dust clouds sit in front of bright stars. Those lanes matter because they hide parts of the galaxy, while leaving other paths almost transparent, carving out narrow windows with a clearer view into and above the disk. HLX-1 lies in one of these more open sight lines high above the main starry band, where the foreground dust is present, but thinner along the line between source and observer. Through optical telescopes, the surrounding star cluster appears as a modest, compact patch of light, slightly bluish compared with the older, redder stars in the bulge. That bluer tone quietly hints at younger stars or ongoing star formation in the cluster, perhaps linked to the history of the stripped companion that carried HLX-1 into the halo. The contrast between the small bright knot and the softened background of the galaxy makes the region easier to pick out. At the same time, dust within and around the cluster dims and reddens some of its light, acting like a fine veil drawn across the stars. Ultraviolet observations add another layer to this picture. Ultraviolet light is particularly sensitive to hot young stars and to the way dust scatters shorter wavelengths. In areas where dust is dense, ultraviolet light suffers more strongly and can almost disappear, but where the dust thins, it escapes with fewer losses and traces recent or ongoing star formation. Around HLX-1, ultraviolet maps highlight the cluster and any nearby knots of young stars with extra clarity, showing that this off-nuclear region is not entirely old and quiet. These ultraviolet hints matter because they support the idea that the passage and stripping of a small galaxy compressed gas and triggered new stars near the black hole. As attention moves to X-rays, the influence of dust changes character. X-rays have much higher energy and pass through most dust grains with only gentle absorption, so thick veils that block optical light hardly disturb the hardest X-ray photons. In X-ray images, the bright point source of HLX-1 stands out strongly against a much smoother galactic background. The host disk and bulge almost vanish, leaving the black hole and its immediate surroundings as the dominant feature. This difference between optical and X-ray scenes helps separate the behavior of the black hole from the structure of the galaxy. The optical image reveals where stars and dust sit, while the X-ray image reveals where gas falls inward and heats near HLX-1. Together they tell a calm story about a black hole tucked into a mixed environment of young and old stars, diffuse gas and patchy dust. Radio observations add another quiet perspective. At longer radio wavelengths, cold gas and diffuse jets become easier to detect while dust no longer blocks the view. Occasional radio flares near HLX-1 hint that during some outbursts, narrow jets or expanding bubbles of energetic particles may form. Although these signals are faint and rare, they matter because they link the inner accretion flow with the larger scale environment. They suggest that HLX-1 does not only receive material, but can also return energy and momentum back into the surrounding medium. Across all these bands, the key idea remains that dust and gas do not simply hide the system. They select the kind of information that each window reveals. Optical and ultraviolet light trace stars and recent star formation while being shaped by dust lanes. X-rays expose the hot inner regions of the accretion flow, cutting through most of the obscuring material. Radio waves carry cues about outflows and about colder gas that might be present in the same region. The combined view is not confusing but complementary. Each band highlights a different layer of the same quiet structure. In the mind's eye, HLX-1 and its cluster can be imagined as a small lantern, suspended above a dim, dusty disk, viewed through several overlapping filters of light. One filter emphasizes the stars around it, another emphasizes the inflowing gas, and another responds to any jets or winds that escape. This multi-band portrait matters because it steadies the interpretation of HLX-1's properties. When many windows agree on its position and behavior, the case for an intermediate mass black hole grows stronger. As the story moves inward, the focus shifts from the ways light escapes to the ways the black hole's brightness changes with time. Those changes, recorded in long patient monitoring campaigns, carry the imprint of the accretion flow itself and guide the next step in understanding HLX-1. In the region directly around HLX-1, the most revealing signal is not a single snapshot, but how its brightness drifts with time. The core idea is that HLX-1 brightens and dims in a slow repeating rhythm, and that rhythm carries clues about how gas falls inward. When HLX-1 was watched over many years, its X-ray light was seen to rise and fall rather than remain steady. It grows brighter over months, reaches a strong peak, and then declines again into a quieter phase, with this pattern repeating on roughly yearly timescales. Each outburst shows a gentle climb, a calm crest, and a long, soft fading tail. This behavior resembles that of smaller black hole systems in the Milky Way, simply stretched in brightness and in overall scale. That similarity matters because it suggests that HLX-1 follows the same basic rules of accretion, even though its mass sits in the intermediate range. During the brighter intervals, the X-ray spectrum becomes softer, meaning the typical photon energy shifts towards slightly lower values. A softer spectrum usually points to a thick, efficient accretion disk, where gas spirals inward smoothly and radiates from a broad, bright surface. During the fainter phases, the spectrum becomes harder, with higher energy photons more common in the emission. A harder spectrum is often linked with the thinner disk and a stronger, hotter corona of energetic particles close to the black hole. These long, gentle swings between soft and hard states are known as spectral states, different stable arrangements of the inner flow. Their presence in HLX-1 and their link to the outburst provide a calm but powerful clue about how the rate of gas supply changes. In the soft state, the disk contributes most of the light, and the variations look smoother and more regular. In the hard state, the corona becomes more important, and there may be brief hints of narrow jets or broader winds. The roughly yearly cycle between these states points toward a slow change in how much gas reaches the inner disk over that time. One way to imagine this is to picture the fuel supply arriving in gentle pulses, perhaps guided by the orbit of a companion star, or by slow instabilities far from the center. When a new pulse of gas reaches the inner regions, the disk fills, cools slightly, and brightens, deepening the soft X-ray emission. As the supply drops, the disk thins, the corona gains relative strength, and the overall spectrum gradually hardens again. Over many cycles, the timing of these changes becomes a quiet weighing scale for the central mass. Processes such as disk build-up, spreading, and cooling all take longer in systems with larger gravitational radii. In HLX-1, the long timescales of the outbursts and the high luminosity fit an object with a mass of tens of thousands of suns. This estimate matters because it supports the picture of HLX-1 as a genuine intermediate mass black hole, rather than a smaller object seen under special conditions. In this way, the light curve, the measured brightness over time, turns into a steady measuring tool instead of simple decoration. Its shape over months and years provides a non-intrusive way to infer the size and structure of regions very close to the black hole. The flickering that emerges from this record is not wild or unpredictable. It settles into patterns that can be anticipated once the basic cycle is understood. Small departures from the average behavior then carry extra information about local changes in density, temperature, or magnetic structure within the inner flow. During some transitions, faint radioactivity suggests that a jet or wind may briefly form and carry part of the inflowing energy back outward. In those moments, HLX-1 behaves not only as a sink that swallows matter, but also as a modest source of feedback to its surroundings. Even with this added complexity, the overall changes remain smooth on human timescales, with no sharp spikes or violent breaks. The system drifts from one state to another over days and weeks rather than in sudden jumps. That smooth behavior supports the view that HLX-1 is fed by slow, steady processes in its outer environment, with only mild variations in the fuel supply. It paints the image of a calm engine running in a regular cycle rather than an erratic flare source. From far away, the timing story of HLX-1 can be pictured as a gentle breathing in light. It brightens as the disk fills and cools, then dims as the inner regions heat and thin. This repeated motion anchors more detailed models of the accretion flow and constrains how large the disk can be. As the narrative moves inward, attention gradually shifts from the rhythm of the flickers to the shape of the disk that produces them. In that inner region, radiation, rotation, and gravity act together, arranging the flow into a slowly whirling layered structure around HLX-1. In the inner regions around HLX-1, the bright X-ray rhythm described earlier is produced by a broad, slowly turning structure of gas. Most of the light comes from a rotating layered flow called an accretion disk. This flow behaves like a dim hot whirlpool rather than a storm. An accretion disk is a rotating ring of gas falling inward. Close to HLX-1, that ring spreads into many nested rings, each circling at a slightly different speed. As neighboring rings rub past one another, they share energy and gradually lose some of their orbital support. In this gentle trade-in of energy, gas slides inward, warms and radiates, turning gravitational pull into steady light. The inner disk near HLX-1 can be pictured as a flattened, glowing plane, hotter at the center and cooler toward the outer edge. This temperature gradient matters because it shapes the spectrum that observers measure. Softer X-rays arise in somewhat cooler zones, while harder photons emerge closer to the center. The structure is not solid. It is more like a very thin hot mist arranged in a circular pattern. In the high state, when HLX-1 shines more softly in X-rays, the disk is thought to be thick enough and bright enough to dominate the emission. In that phase, the gas distribution is smoother, and the temperature changes gradually from the inside outward. The result is a spectrum that looks like overlapping contributions from many warm rings. The nearly regular shape of that spectrum helps set the scale of the disk and with it the approximate mass of HLX-1. A more massive black hole cools the disk at a given luminosity because the emitting area can be larger and the gravitational field deeper. These relationships matter because they provide a quiet, indirect weighing method based only on the color and brightness of the light. At larger radii, the disk blends into the surrounding environment, where cooler gas from the circumgalactic and interstellar media slowly joins the flow. In those outskirts, the gas is cooler and thicker, more like a hazy funnel that feeds the hotter inner sheet. Small irregularities in the supply here can later appear as gentle variations in the brightness of the inner zones. In this way, the accretion disk records both local physics and distant disturbances, acting like a memory surface for the system, within the disk pressure, rotation and gravity balance in a very delicate way. If rotation was stronger, gas would remain on nearly circular paths and little would drift inward. If gravity alone acted, material would plunge too quickly to radiate much energy before crossing the horizon. The presence of subtle friction between rings, often described as viscosity, provides the gentle sideways push that lets gas move inward without breaking the disk apart. In this context, viscosity means friction between nearby rings of gas. It likely comes from tangled magnetic fields and small-scale motions that stir the gas and transfer angular momentum outward. Angular momentum is the tendency of a rotating object to keep spinning. As angular momentum moves outward through the disk, some material at larger radii can move slightly farther out while material closer in loses support and sinks. That slow inward sink heats the gas and boosts the radiation from the inner rings. The disk therefore acts as both a conveyor and a heater, guiding gas toward HLX-1, while gradually converting orbital energy into X-ray light. Near the innermost parts of the disk, the flow changes character. Orbits become less stable, and there is a final radius inside which circular paths can no longer exist. Beyond this point, gas falls inward more rapidly, carrying its remaining energy across the unseen horizon. The inner edge of the bright disk lies near this boundary. Its exact location depends on the mass and spin of HLX-1, so observing how sharply the emission turns over at high energies can constrain those properties. Even without exact numbers, the existence of a clear inner edge reinforces the picture of a compact heavy object with a well-defined gravitational grip. To a distant observer, the disk appears as a small hot rotating patch of light diluted by distance. Its slow changes over months reflect adjustments in the fuel supply and in the internal balance between heating and cooling. Despite the extreme conditions near the center, the overall behavior remains ordered with no need for sudden disruptions. The flow is constant enough that models developed for much smaller systems can be scaled up and applied here. That continuity matters because it links HLX-1 smoothly to a wider family of accreting black holes across the universe. As attention moves closer to the center, focus shifts from the relatively dense disk to the more tenuous high-energy region above and below it. In that region known as the corona, very energetic particles reshape the spectrum and may help launch weak jets or winds from the neighborhood of HLX-1. In the region just above and below the bright disk around HLX-1, a more tenuous structure of very energetic particles hovers, like a faint restless halo. The simple idea is that this high-energy cloak called the corona reshapes the light from the disk and may help drive gentle outflows. While the disk supplies much of the soft X-ray glow, the corona imprints a harder, more energetic component on the spectrum. It scatters and boosts some of the disk's photons to higher energies, turning smooth thermal light into a broader, subtly distorted pattern. In calm language, the corona is a sparse cloud of electrons and other charged particles heated to extreme temperatures. These particles move quickly and interact with the softer photons rising from the disk surface. When a low-energy photon meets a very energetic electron, it can leave the encounter with a higher energy than before. This process, known as upscattering, builds the hard tail seen in the X-ray spectrum of HLX-1. The amount of hard light and its precise shape reveal how strong and compact the corona is at any given time. In the lower, brighter state, when the disk dominates, the corona may contract into a relatively small, dense region near the black hole. In that configuration, the scattering is strong but occurs over a compact zone, so the hard emission rides on top of a very luminous soft component. In the dimmer, harder state, the corona likely becomes more extended and comparatively stronger than the disk. The disk may thin out or retreat slightly, while the high-energy cloud takes over more of the emission. This shift matters because it tracks how the flow of energy within the inner accretion system redistributes itself between cooler layers and the hot tenuous envelope. Somewhere within this, corona magnetic fields thread the gas in tangled loops. They rise and reconnect, releasing energy in many small frequent events, rather than in a few dramatic flares. That repeated release gently heats the particles and maintains the corona against cooling. In this view, the inner regions around HLX-1 resemble a softly lit workshop of magnetic activity, steady rather than chaotic. The corona sits between the disk and the vacuum of intergalactic space, mediating the escape of radiation and at times of mass. When conditions are right, part of the coronal gas can be guided along ordered magnetic field lines and launched outward as a narrow jet. At other times, broader, slower winds may lift off from the upper disk layers and join the surrounding medium. Occasional radio flares and subtle changes in the spectrum whisper that such outflows sometimes occur in HLX-1. They are not constant, but they leave hints of a link between changes in the corona and the appearance of moving plasma farther away. Even when no clear jet is present, the presence of a hot scattering layer changes how the disk is seen. Some photons that would have left the disk directly instead take detours through the corona, emerging with altered energies and directions. This mixing smooths out small variations and can spread sudden changes over slightly longer times. The result at large distances is a light curve that appears calmer and more rounded than the raw activity near the event horizon. In addition, the corona can cast a kind of X-ray echo onto the disk itself. Hard photons that travel downward strike the cooler material below, where part of their energy is absorbed and re-emitted at different energies. This reflection imprints subtle features on the spectrum, such as broadened lines and gentle curvature at certain energies. These imprints matter because they carry information about the geometry of both the corona and the inner disk. In HLX-1, even partial measurements of these signatures help confirm that the emitting region is compact and strongly curved by gravity. They support the picture in which a sizable black hole sits at the center of a luminous layered structure. Over many cycles, the corona responds gently to changes in the inflowing gas. When the supply rises, it softens and draws closer to the disk. When the supply falls, it becomes more rarefied and extends farther out, leaving a harder glow. These adjustments take place over timescales long enough that the overall behavior remains smooth and predictable. To the imagination, the corona around HLX-1 can be pictured as a thin, glowing mist wrapped close around the inner disk, brightest near the center and fading outward. It is not a solid shell, but a continuous changing environment, where particles, fields, and photons interact in a quiet but constant exchange. The interplay between disk and corona explains why the spectrum of HLX-1 changes with state, and why some phases favour soft light, while others favour hard. As the journey proceeds, attention turns inward again toward the last stable orbits near the black hole. In that innermost region, the geometry of space-time itself begins to govern what kinds of orbits are possible, and how close matter can circle before it must fall in. In the immediate surroundings of HLX-1, some of the most delicate clues about its influence do not come from inflowing gas, but from matter that escapes. The central idea is that a small part of the energy released near the black hole does not simply vanish into light. It also helps to lift and guide streams of plasma away from the disk, forming weak jets or broader winds that touch the nearby environment. When HLX-1 is monitored during changes between bright and faint states, hints of radio emission appear at certain times. These faint signals suggest that as the corona and disk rearrange themselves, narrow, fast-moving flows may be launched from the inner regions. Each episode is modest on a galactic scale, yet over long periods the combined effect can gently reshape gas near the system. In smaller black hole binaries, changes from a soft state to a hard state are often the moments when compact jets appear. By analogy, similar transitions in HLX-1 may create quiet periods of jet activity, even if the details remain blurred by distance. In this calm picture, a jet is not a violent spear but a slender, persistent beam of particles and fields threading its way through the surrounding gas. As it moves, it can carve a low-density channel, reducing the amount of matter directly in the path and heating the edges of the cavity. The energy deposited in these edges can keep nearby gas warmer and more stirred than it would otherwise be. Over millions of years, such mild heating helps maintain the circumgalactic and interstellar media in a gently excited state. In addition to narrow jets, broader winds may rise from the upper layers of the disk or from the base of the corona. A wind in this context is a more diffuse outflow of gas pushed outward by radiation pressure, magnetic forces, or thermal expansion. While each parcel of gas in the wind only carries a small share of mass, the steady flow can reach large distances from the black hole. It distributes both energy and enriched material back into the cluster and the wider halo. Some of the gas that once fell inward and passed through the inner disk may thus return to the environment in altered form. That recycling matters because it changes the chemical and thermal conditions around HLX-1, influencing future star formation and the behavior of any newly arriving gas. In the compact star cluster that likely surrounds HLX-1, these outflows can act as a gentle regulator. They may clear small low-density bubbles around the core, push on nearby clouds, and keep fresh infall from piling up too quickly. At the same time, the energy input is limited enough that it does not strip the entire region of gas. Instead, it balances accumulation and removal in a way that encourages long-term moderate accretion. In this balanced state, HLX-1 neither chokes on an excess of fuel nor starves in a perfectly empty cavity. It feeds in a rhythm guided by the broader environment, but also adjusted by its own feedback. On slightly larger scales, outflows from HLX-1 mix into the gas that threads the outer parts of ESO 24349. In these outskirts, the density is low, and the gravitational pull of the galaxy is still strong but not overwhelming. Jets and winds entering this region can spread their momentum and heat over large volumes without disrupting the overall structure. The result is a very gentle stirring that helps keep gas from cooling and collapsing too quickly. This process connects HLX-1 to the slow evolution of its host. Even though the power of its outflows is modest compared with that of a central supermassive black hole, their effect is focused in a smaller volume, where relative changes can still be important. The black hole and its cluster become a small but persistent engine of local feedback, tuning the conditions in a patch of the galactic halo. To an observer imagining this from afar, the space around HLX-1 can be seen as a quiet workshop of inflow and outflow. Gas spirals inward through the disk heats near the event horizon, and then leaves partly as light and partly as gently moving streams. Those streams trace faint paths through the surrounding medium, leave behind warmed shells, and gradually merge with the broader flows of the halo. Across many cycles, this exchange helps ensure that the story of HLX-1 is not only about swallowing, but also about giving back. The next inward step, however, leads away from these larger motions and down toward the final stable orbits near the black hole. In that inner zone, space-time curvature takes over from ordinary orbital mechanics and sets a last boundary for matter that still circles safely around HLX-1. There, the flow becomes thinner, faster, and more closely tied to the exact mass and spin of the central object. Close to HLX-1, the flow of gas enters a region where familiar orbital instincts begin to fail. The key idea is that stable circular paths eventually end. Beyond a certain point, matter can no longer orbit safely, and must instead spiral inward with increasing speed. This threshold is known as the innermost stable circular orbit, often shortened to ISCO. It is not a physical ring that can be touched, but a mathematical boundary in space-time. Outside this radius, gas can circle the black hole in nearly steady loops. Inside it, even the slightest disturbance sends matter plunging inward. For a non-spinning black hole, the ISCO sits at a particular distance measured in gravitational radii. If the black hole spins, that distance changes. For orbits moving in the same direction as the spin, the ISCO moves inward. For orbits moving against the spin, it shifts outward. This dependence matters because it means the structure of spacetime near HLX-1 quietly encodes information about its rotation. The inner edge of the bright accretion disk naturally settles near the ISCO. Gas further in spends too little time in orbit to radiate strongly before crossing the horizon. As a result, the disk's luminous surface effectively ends around that radius. Observers cannot see the ring directly, but they can sense its location through the shape of the spectrum. Emission from inner regions tends to be hotter and more strongly affected by relativistic effects. As the disk extends closer to the black hole, the soft component of the spectrum shifts and changes slope. In HLX-1, the temperatures and luminosities measured during its high, soft state point toward a disk that reaches close to this innermost region. The exact fit depends on both mass and spin, but in broad terms the ISCO appears relatively compact compared with what would be expected for a much smaller stellar black hole at the same luminosity. This impression supports the view of HLX-1 as a heavier object with a deeper well carved into spacetime. To imagine this region, it helps to picture a series of circular tracks shrinking toward a central point. Far out, the tracks are wide and gently curved with orbital speeds, moderate and gravity strong but familiar. Closer in, the tracks become tighter, speeds increase, and time dilation grows stronger. Near the ISCO, the last track suitable for a circular orbit appears. Inside it, the tracks are no longer stable. Any object attempting to follow one will gradually drift inward and spiral away. Gas in the accretion disk approaches this boundary, while still radiating steadily. Its orbital motion combined with gravitational redshift broadens and skews spectral features. Photons emitted from gas moving toward the observer are blue-shifted, while those from gas receding are red-shifted. Gravity then pulls on all photons, leaving the deep potential well shifting them to lower energies overall. The combination of motion and gravity creates a gentle smear in energy space. Even without sharp lines, this smear leaves a characteristic imprint on the observed spectrum. In HLX-1, the spectrum's curvature hints at a disk extending into a region where relativistic effects are non-negligible. That hint matters because it implies that the bright part of the disk lies close to the ISCO, not far outside it. Gas just outside this radius remains in orbit for many cycles, losing energy gradually through internal friction and radiation. As it does, it drifts inward ring by ring until it crosses the ISCO and can no longer maintain a circular path. From that point inward, the flow becomes more like a smooth plunge. The material still carries angular momentum, so it does not fall perfectly straight. However, the radial motion becomes dominant. The time available for radiation shrinks, and most of the remaining energy is carried across the horizon. To a distant observer, this plunging region appears dim compared with the outer disk. In a mental image, the ISCO marks the inner rim of a softly glowing disk with a darker, less luminous zone inside. The position of that rim depends on the spin of HLX-1, which twists space-time around it in a subtle way. Spin causes a phenomenon known as frame dragging, where space-time itself is gently pulled around in the direction of rotation. Near a fast-spinning black hole, this effect influences how orbits behave. Co-rotating orbits can exist closer in, while counter-rotating orbits feel stronger resistance. In HLX-1, the precise spin remains uncertain, but the possibility of significant rotation adds another quiet layer of structure to the inner flow. It shapes how the disk aligns, how the corona forms, and where stable orbits end. Over long periods, these details influence how efficiently HLX-1 converts infalling mass into light. A disk reaching closer to a fast-spinning black hole can release more energy per unit mass than one around a non-spinning object. Even without numbers, this idea connects the observed brightness and spectral shape to the geometry of space-time near the horizon. The innermost stable circular orbit therefore acts as a bridge between observation and theory. It is inferred, not seen yet. Its presence gently organizes the inner accretion flow around HLX-1. The story of the ISCO is one of boundaries rather than edges of orbits that can exist only up to a certain depth in the gravitational field. As the narrative moves still closer to the center, attention turns from gas and orbits to light itself. In that next layer, the paths taken by photons near HLX-1 become bent and folded by curvature, raising the question of how light would travel if it skimmed the very edge of this deep well. In the region just inside the bright inner disk of HLX-1, gravity begins to steer not only gas, but also the paths of light itself. The key idea is that photons leaving this area do not travel in straight lines, but follow gently curved tracks through space-time. Some of these tracks skim close to a notional surface called the photon sphere, where light can circle the black hole on almost closed orbits. A photon sphere is the region where gravity is strong enough to bend light into nearly circular paths, rather than letting it escape directly. For a non-spinning black hole, this surface sits outside the innermost stable circular orbit, while spin can shift its position slightly inward or outward. In HLX-1, the photon sphere is far too small and distant to be imaged directly, yet its presence still matters for how the system appears. Photons that pass close to this region can loop partway around the black hole, before finally escaping toward distant observers. Each loop stretches the path length and changes the amount of gravitational redshift those photons experience. Gravitational redshift means that light climbing out of a deep gravitational well loses energy and shifts to longer wavelengths. In practical terms, photons that venture deeper come out slightly softer and delayed compared with those that leave from farther away. This mixture of path lengths and energy shifts quietly broadens features in the spectrum of HLX-1. It does not create sharp rings in current images, but it gently redistributes light across energies and directions. Some photons that would have missed the observer in flat space are bent into view while others are pulled away. This bending is a form of gravitational lensing where mass acts like a transparent lens that redirects light. Around HLX-1, strong lensing near the photon sphere shapes the innermost light, and weaker lensing farther out influences how the disk and corona appear on large scales. If HLX-1 were much closer, a sufficiently sharp telescope might see a thin, bright ring formed by strongly lensed photons. Such a photon ring would outline the shadow cast by the event horizon against background light. For HLX-1, distance and limited angular resolution make this ring far too small to resolve. The expected image on the sky is effectively a single unresolved point of X-ray light. Even so, ideas developed for nearby supermassive black holes still help interpret the behavior of HLX-1. They show how lensing and redshift combine to hide some zones and emphasize others, even when everything blends into one point in a telescope. In models of HLX-1, light rays are traced backward from the observer through curved space-time to the disk and corona. These ray tracing studies reveal which parts of the inner flow contribute most strongly at different energies. Regions near the approaching side of the disk can appear brighter because their motion blue shifts photons and directs more light toward the observer. Regions on the receding side appear dimmer and more redshifted. Gravity wraps these zones partially around the black hole, creating overlapping contributions that soften any sharp pattern. Over long observing times, the combined effect is a smooth, stable profile rather than a flickering, sharply structured image. Small changes in the inner flow or in the corona's size can still leave signatures in the overall spectrum and timing. They change which photon paths are most populated and how strongly redshifted or blue-shifted those photons become. In turn, these changes help refine estimates of HLX-1's mass and spin. While no direct picture of a photon ring is available, the same physics underlies the shapes of spectral features and the times at which different energies vary. This link matters because it ties interpretations of HLX-1 to a broader framework tested in other systems. It allows intermediate mass black holes to be studied with tools originally built for giants in galactic centers. Looking ahead, future observatories with sharper timing and energy resolution may pick out subtle echoes caused by light taking different paths near HLX-1. Some photons circle closer, arriving slightly later and at different energies than those traveling more direct routes. These gentle echoes would be too small to form visible rings, yet large enough to influence the detailed pattern of flickers. They would add a faint extra layer of structure to the calm breathing rhythm already seen in the light curve. Such details would not change the overall impression of stability, but they would sharpen the picture of how curved space-time guides light near the black hole. Whether or not such fine structure is ever measured for HLX-1, the concept of curved photon paths brings the picture of its inner region into focus. Light does not simply leave the disk and corona, it weaves through a curved landscape before reaching intergalactic space. As the journey continues inward, attention turns to the boundary beyond which no photon path can ever emerge. That final surface, the event horizon, marks a quiet edge where the observable story of HLX-1 naturally comes to a close. In the deepest region of HLX-1's gravitational influence, the story of matter and light arrives at a quiet boundary. The central idea is simple and gentle. There exists a surface beyond which no signal, not even light, can return. This surface is the event horizon, a one-way frontier rather than a solid shell. Outside it orbits, and radiation still exists, though shaped by strong curvature. Inside it, paths all lead inward, and the distinction between directions gradually loses meaning. For HLX-1, the event horizon surrounds roughly 20,000 solar masses, compressed into a region far smaller than any star. Its size in kilometers remains tiny compared with the scale of the host galaxy, yet in its immediate neighborhood the horizon defines the final contour of space-time. Everything that happens in the accretion disk, the corona and the photon sphere, unfolds just outside this contour. In that sense, the horizon does not act as an active surface, but as a calm limit that structures the entire scene around it. Matter spirals toward this boundary after losing the support of stable circular orbits near the innermost stable circular radius. In the final approach, the flow becomes more like a smooth plunge than a whirl. Gas still carries angular momentum, so it continues to swirl, but the inward component of motion now dominates. To a distant observer, the last stages of this plunge appear slowed and softened by time dilation and redshift. Signals from material close to the horizon lose energy and stretch out in time. Eventually they fade below detectability, leaving only the steady glow from slightly more distant regions. The horizon itself neither glows nor reflects. It quietly absorbs whatever crosses it. This quiet absorption matters because it ensures the stability of the external picture. There is no bouncing or ringing at the surface, no solid crust to crack or flare. Once energy and matter cross the horizon, their detailed histories are hidden from the outside universe. All that remains to characterize HLX-1 are a small set of macroscopic quantities such as mass and spin. This simplicity turns the horizon into a remarkably clean concept. Despite the complex processes in the surrounding gas, the central object remains defined by just a few parameters. In that way, HLX-1 behaves like other black holes across the universe, whether they sit in X-ray binaries at the centers of galaxies or in drifting intermediate mass systems. The event horizon provides a common language that unifies them. For listeners picturing this region, it can help to imagine the horizon not as a wall, but as a very still shoreline in space-time. Waves of light and matter in the outer regions roll inward, changing shape as currents and winds guide them. At the shoreline they simply do not return. Nothing dramatic is required at that boundary. The striking part is not a sudden explosion but the final absence of outbound signals. Even so, the presence of the horizon leaves fingerprints in the light seen from afar. The existence of a one-way surface changes how infalling gas radiates, since the deepest zones contribute less to the observed glow. Comparisons between HLX-1 and systems where matter falls onto a hard surface show that a horizon fits the data more comfortably. In hard surface models, material would crash onto a dense core and release extra energy very near the center. That extra energy would brighten certain spectral components and alter the long-term behavior of the light curve. HLX-1 instead behaves more like a true black hole, with emission patterns consistent with energy being lost beyond reach, rather than radiated back from a surface. Over long time scales, this quiet drainage of mass and energy across the horizon shapes the growth of HLX-1. Each infalling parcel adds a little to the mass and, depending on its angular momentum, adjusts the spin. The horizon expands or reshapes imperceptibly, with each addition always remaining cloaked from direct view. The environment responds indirectly through subtle changes in the depth of the gravitational well and in the efficiency with which future infall can radiate. The horizon therefore acts as an invisible bookkeeping boundary for the system's history. All the gas and radiation that ever interacted with HLX-1 either escapes to infinity or ends up recorded inside this boundary. The observable story stops at the outer side of this surface. Beyond it, current theories still describe the broad outline but lack direct tests. In the context of HLX-1, that uncertainty does not introduce menace. It simply marks the limit of what needs to be known to interpret the light. The existence of a horizon allows the focus to remain on regions where observations can reach from the large-scale environment down to the innermost stable orbits. From there, the narrative can now ease outward again. The next step looks at how the extreme gravity around HLX-1 influences the flow of time and the bending of light, as seen from far away, connecting the quiet inner boundary to the wider, slowly changing universe in which this intermediate mass black hole drifts. Seen from far away, HLX-1 sits in a region where time and light do not behave quite as they do in open space. The core idea is calm and precise. The presence of a deep gravitational well means that clocks closer to the black hole tick more slowly, and light rays follow gently curved paths. This effect is called gravitational time dilation. A clock resting deep in the potential well of HLX-1, for example, on a small platform orbiting the inner disk, would measure intervals that differ from those measured in the cluster or in intergalactic space. To that inner clock, each second feels normal, steady, and unremarkable. To a distant observer, though, processes near the black hole seem to unfold more slowly than similar processes far away. As matter spirals inward, its emission is affected by this slowing of local time. Flickers produced close to the horizon appear stretched when they reach a far-off telescope. Rapid changes are muted, and the observed pattern becomes smoother. This stretching matters because it helps to explain why the light from HLX-1, although coming from extremely fast-moving gas, shows variations on timescales that still feel gentle on human scales. Time dilation works together with gravitational redshift. Light climbing out of the deep potential well loses energy sliding to longer wavelengths. Photons that start near the inner edge of the disk arrive a bit softer and slightly delayed compared with those that leave from farther out. In the combined light curve, small bursts blend into broader, calmer features. Meanwhile, the extended halo star cluster and galaxy around HLX-1 sit in shallower parts of the gravitational landscape. Clocks there tick slightly faster than clocks near the horizon, but still a little slower than clocks in empty intergalactic space. The result is a smooth gradient of ticking rates from the deep well, near the black hole up through the cluster, the galaxy, the group, and out to the cosmic background. This gradient is not something everyday senses can feel, yet it shapes how long events appear to last when viewed from different vantage points. On larger scales, the mass of HLX-1 and its cluster also bends light passing nearby. This bending is another form of gravitational lensing, but it is gentle rather than dramatic. A beam of light from a distant background galaxy drifting close to HLX-1 would have its path deflected by a tiny angle. The deflection would be too small to form vivid arcs or multiple images. The mass simply is not large enough compared with cluster scale or galaxy scale lenses. Even so, the principle is the same. Mass tells spacetime how to curve and curved. Spacetime tells light which paths to take. In the environment of ESO 24349, lensing by HLX-1 is submerged beneath the broader lensing produced by the galaxy and the group as a whole. Their combined mass gently magnifies and distorts background sources. HLX-1 then adds only a small local contribution, like a slight ripple on a much larger slow ocean swell. For practical observations, this means HLX-1 does not stand out as a strong gravitational lens. Its influence shows up instead in how it shapes the light produced in its own immediate surroundings. The bending of photon paths near the inner disk discussed earlier is one manifestation of this. As photons weave through curved space-time, some are directed toward the observer who would not otherwise see them. others are bent away. Together with time dilation and redshift, this subtle choreography sets the detailed brightness and spectrum of HLX-1. It also influences how quickly the brightness seems to change. Short, sharp variations near the horizon are smoothed and delayed, while broader trends originating farther out remain closer to their original shape. The net effect is a light curve that feels like a slowed, softened version of the raw interactivity. For HLX-1, these relativistic effects are not an exotic garnish, but part of the basic functioning of the system. They decide how much of the energy released near the black hole escapes as radiation, and how that radiation looks when it finally reaches distant detectors. They also link the local physics around HLX-1 to the broader expansion of the universe, since all observed time intervals and energies are measured against a cosmic backdrop. The gentle stretching of time and bending of light do not break the overall calm of the system. Instead, they act like a soft filter that sits between the inner engine and the open sky, slightly reshaping everything that passes through. In a mental image, HLX-1 can now be seen as a quiet well in space-time, its sides lined with luminous gas, and its rim veiled by a thin mist of curved light paths and slowed clocks. Beyond this well, the galaxy, the group, and the large-scale structure of the universe continue almost unaffected their own motions, unfolding on even longer timescales. The final step of the journey returns to that broader view, gathering the clues from environment, accretion, and relativity into a single present-day picture of what HLX-1 reveals about black holes that live between galaxies. From the wider scales down to the deepest orbits, the picture of HLX-1 now settles into a calm, complete scene. The simple message is that one off-nuclear point of light can quietly trace an entire chain of structures, from galaxy cluster and halo down to event horizon, and curved photon paths. HLX-1 does not sit alone. It occupies a gentle crossroads where the group environment, the circumgalactic medium, the host galaxy, and a compact star cluster all overlap. In that shared region, slow tides, thin streams of gas, and the memory of an earlier merger work together to feed and guide this intermediate mass black hole. Its likely origin, as the stripped core of a small companion galaxy, ties the system to the long history of hierarchical growth. Over time, larger galaxies gather smaller ones, folding them into their halos and disks. HLX-1, with its surrounding cluster, appears as one preserved fragment of that process, still carrying a heavy central engine. This origin story matters because it provides a gentle route for seeding black holes between the tiny and the enormous, without requiring rare or violent events. The environment around HLX-1 supports this interpretation in several ways. The extended halo hosts faint streams of stars and gas, the circumgalactic medium supplies slow inflows, and the outer disk and bulge of ESO 24349 frame an off-plane, off-center orbit. Dust lanes and multi-purpose viewing windows then decide which parts of this structure become visible in different kinds of light. Optical and ultraviolet bands highlight the compact star cluster X-rays, reveal the accretion flow, and radio hints mark occasional outflows. Together, these bands weave a multi-layered portrait of a black hole embedded in a living environment, rather than placed in isolation. Moving inward, the long-term monitoring of HLX-1's brightness turns its flickering into a precise patient tool. The gentle rise and fall of its outbursts, the change between soft and hard X-ray states, and the broad shapes of those cycles all point toward a disk and corona feeding a central mass of around 20,000 suns. The timescales involved are longer than in small binaries, yet shorter than in enormous galactic nuclei, matching expectations for an intermediate mass object. This match matters because it supports a continuous sequence of black hole sizes, rather than a sharp gap between stellar and supermassive scales. The inner accretion structure adds further weight to this quiet argument. A luminous multi-temperature disk approaches the innermost stable circular orbit, converting gravitational energy into light as gas slowly spirals inward. Above and below that disk, a hot variable corona reshapes the spectrum and at times helps launch narrow jets or broader winds. These components mirror those in other accreting systems scaled to the particular mass and environment of HLX-1. They show that the same basic rules of accretion can operate across a huge range of masses and settings. Even the unseen layers near the ISCO photon sphere and horizon leave their traces in the observed light. Relativistic broadening, gravitational redshift, and time dilation all work together to soften sharp features and stretch vast variations into the smoother patterns actually measured. Although no direct image of a photon ring or shadow is possible at this distance, the same physics that shapes such images still governs HLX-1. Curved paths for light and slowed clocks near the horizon become part of the quiet machinery that links theory and observation. For HLX-1, the observational limit arrives well before the eye can resolve any of these inner structures. Telescopes register a point-like source whose brightness and spectrum change over months and years, backed by faint traces of a star cluster and host galaxy. In that simple point, however, lies the compressed record of everything described so far. Cluster tides, halo, dynamics, gas pathways, disk structure, coronal heating, outflows, relativistic geometry and horizons all leave their signatures in how the point brightens, softens, hardens and fades. This convergence matters because it shows how far careful observations can reach without ever seeing the black hole directly. By watching a single source through many windows and over long durations, astronomers can infer the presence of an intermediate mass black hole drifting between galaxies. HLX-1 therefore becomes a teaching case for how to recognize similar objects elsewhere. It suggests that other galaxies may host off-nuclear engines of comparable mass hiding among their halos and outskirts, marked only by occasional calm surges of X-ray light. Each such system would carry its own story of mergers, stripping and gentle feedback into the surrounding gas. Looking ahead, future observatories with sharper timing, broader energy coverage and improved sensitivity may refine the picture. They might resolve finer echoes in the light curve, detect subtler signatures of winds, or constrain the spin of HLX-1 more tightly. Yet even without those details, the present view already reaches a satisfying restful closure. HLX-1 stands as a clear example of an intermediate mass black hole shaped by its environment, and in turn shaping that environment in quiet ways. From the vantage point of a distant listener, it is enough to hold the scene as one continuous layered structure. A thin, edge-on galaxy crosses the darkness, its halo bathed in faint gas and star streams. Above the plane, a compact cluster wraps a black hole whose mass sits between stellar and supermassive scales. Around that black hole, disks, coronae, and curved light paths do their work just beyond an unseen horizon. Beyond all of this, the galaxy group and cosmic web continue to evolve while HLX-1 remains a steady patient marker of how gravity sculpts matter on every scale. At this observational limit, the narrative rests, leaving HLX-1 as a quiet beacon between galaxies carrying within its light a complete, gently told story of environment, growth and space-time. In the quiet outskirts of a distant galaxy, the full picture of HLX-1 now feels settled and calm. A thin, edge-on disk crosses the darkness wrapped in a faint halo of stars and gas, and above that disk a single, persistent point of high-energy light marks the place where an intermediate mass black hole slowly feeds. Around it, a compact cluster of stars drifts through the halo, carrying the memory of an earlier small galaxy that was gently stripped and folded into ISO 24349. Farther out, the group environment, the circumgalactic medium, and the soft intracluster gas form wide, slow pathways that guide matter inward. On smaller scales, gas slides into a disk heats near the center, and releases its energy as a smooth rhythm of X-ray outbursts. A thin corona hovers above the disk, shaping the spectrum, and at times lifting light streams of plasma back into the surrounding medium as mild winds or narrow jets. Closer still, orbits tighten toward the innermost stable circular radius. Photon paths curve and stretch, and the event horizon waits as a silent boundary beyond which the story no longer needs to be told. Every layer contributes a quiet piece of understanding, from the behavior of halos and minor mergers to the details of accretion and strong gravity. Together they show that HLX-1 is neither an outlier nor a threat, but part of a continuous family of black holes connecting stellar remnants and supermassive giants. Its steady presence between galaxies illustrates how gravity over immense timescales builds and reshapes structure without hurry. Held as a single image in the mind, the scene becomes gentle, a soft web of galaxies, a slender host seen from the side, a small star cluster, and at its heart a mid-sized black hole, whose light rises and falls in a slow, regular breath. From here the narrative can simply rest, letting that layered picture remain in place like a distant, unchanging landmark in the night.